You might have seen this game where people have to sing all the notes in order to win, so it's about time we implement it. As always, you can download the project from GitHub and run it yourself, or just play it online, links in the description. So let's briefly cover what we have in the game. Although it appears to be 3D, the whole game is essentially two-dimensional. The ball can move forward and backward, and also up and down as our voice pitch changes. So we're exclusively concerned about the Z and Y axes. We have a platform, which is just a rectangular cuboid. We have the gates we must pass to win, which are also rectangular cuboids, except they have holes for our ball. Speaking of the ball, we spawn it at 0, 0, 0, which makes all the calculations incredibly simple. In the browser we use WebGL, which gives us the access to 3D rendering with GPU via the canvas element. I won't describe WebGL thoroughly in this video, but it's just the most basic things. A vertex shader to which we pass all the vertices, as well as the standard MVP matrix. Even if you don't know the concept of model view projection, you will see how simple all the transformations are thanks to it. And the fragment shader to which we just pass the color. And that's all our GPU needs to render the game. I intentionally don't use any textures or lighting to keep it as simple as possible, but feel free to add them. You'll need just one library, GL Matrix. This is to seamlessly work with vectors, matrices, and to do the standard MVP operations without reinventing the wheel. So, for example, import the 4x4 matrix. Now, going back to our coordinates, using lookAt, we can define our view matrix with a one-liner, the eye position and where it looks at. As you can see, this will be a fixed position somewhere here. To move our ball, we translate its model matrix, but only by the y-axis so that we see the jumps. For example, a jump by 2 units. Aside from that, the coordinates of the eye and the ball model are always fixed. In other words, the camera tracks the ball along the z-axis. Let's also add the world model, the platform and the gates. To show that the ball moves forward, we translate the world model backward by ball z. And so, if the ball moves 5 units forward, the world model moves 5 units backwards, which reflects the ball movement. And that's how simple it is to render our world. Our gates have a hollow cuboid shape, meaning they have a cuboid hole. It is bigger than the ball so that the game does not feel impossible. I used the laziest possible approach and simply combined 4 cuboids to render a gate. Perhaps not the most efficient, but it simplifies a lot. And this is the example code. Now let's discuss the game mission, which is to sing Solfège. These are all the syllables we have to sing, do, re, mi, fa, sol, la, ti, do. But what exactly are they? Without going too deep into Western music theory, as I'm totally not qualified to do it, suppose we have a piano and its middle C octave. The syllables are representing the labeled white keys from C to B. So if we write down all these 12 notes, including the sharps represented by the black keys, our syllables are meant to be sung with the frequencies of C4, D4, E4, F4, G4, A4, B4. But how do we know these frequencies? First, let's grab the A note from the previous octave, so A3. It has this beautiful round frequency of 220 Hz. Now let's compare it to the A4. It has the frequency of 440 Hz, which is a double. Unsurprisingly, the next octave has A5, also with a double frequency. But here's the thing, this is true for any other note name. For instance, the frequency of C4 is a double of C3, and so is F5 a double of F4, which brings us to the next conclusion. The frequency ratio between any two neighboring notes, C4 and C sharp 4, E4 and F4, F sharp 4 and G4, it's all the same. So the frequency ratio between any two neighboring notes x and y is constant. In other words, the frequencies of notes form a geometric series. If it takes 12 notes to double the frequency, then what is this ratio? It's a 12th root of 2. Multiply it 12 times and you get 2. Okay, so now we can easily map these syllables to frequencies. First, create an array of syllables and the offsets they correspond to in the octave. As you can see, we always jump by 2, except between E4 and F4. Next, use A4 as reference because of its beautiful round frequency. To translate it to the other frequencies, we must know that its offset is 9. And now we can easily map each offset to a frequency. Shift the offset relative to A4 offset, divide by 12, and that's the exponent of 2. Lastly, multiply by our base frequency A4. This is the result and what the player has to sing. The crucial game logic is mapping all these frequencies to a height. For a game to work properly, the same mapping must be used to convert the player pitch to the ball height, as well as the current syllable frequency to the height of the gate hole. If the pitch is the lowest supported one, the ball height is at minimum. If the pitch is the highest supported one, the ball height is at maximum. Suppose these are the ranges for supported frequency and height. Then, what is the height function of frequency? We need to map one value range to another. To do so, I suggest we start by normalizing the frequency, subtract the minimum value and divide by its range of 300. Now, it's a value between 0 and 1. To accomplish a linear mapping, we can multiply that value by 5, our height range. For the minimum frequency of 200, we get 0 multiplied by 5, so 0. For the maximum frequency of 500, we get 1 multiplied by 5, so the height is 5. For the middle frequency of 350, we get a half multiplied by 5, so 2.5. So here's the code doing all that. First, a general rescale function that works for any input range and any output range. Again, normalize the input value, multiply by the output range, and finally add back the minimum output value. Earlier we skipped that step because the minimum height is 0 anyway. And now we can use this general function to obtain our pitch to height function. And that's the complete function to convert a frequency to a height. When we apply that linear mapping to generate gate holes, we will get something like this. This is of course an exponential function as it's based on the exponentially growing frequencies. I'd say such hole placement is just bad. First, there's almost no height progress in the first few nodes, which is very unsatisfying for the player. Second, have you ever seen exponential stairs like this in real life? I'd dare to say a linear placement of the holes would be a much better choice. But in order to achieve it with our frequencies, we have to somehow convert the exponentially growing frequencies to a linear input. What is the magic spell that does it? Of course, logarithm. Let's create a new rescale log function based on our previous rescale. All that's needed is to apply a logarithm to the input scale, so the input value, the input minimum, and the input maximum. And here's our corrected pitch to height function using it. We can use it to create the gates from the scale offsets, like so. Every hole has the height dependent on the pitch, and we just decrease it slightly with a parameter gate hole tolerance so that it's bigger than the ball, as promised. Let's look into the result. As you can see, almost every single hole is about 0.6 above the previous one. The only exception are these two nodes. Here it's just the half because the node offset grows by 1, not by 2, as in all the other nodes. Next topic, audio input in JavaScript. First we must request a permission for the media device. This will result in a pop-up like this. It is a promise because, of course, no one forces us to agree. Okay, next we need an audio context, a media stream source, an analyzer node which we connect to the output of the source, and finally a time buffer. Don't worry about all this, it's just a one-time setup. This is the most important line of the code because we load the actual audio data into our array buffer. We'll perform it every frame. And this is how it looks like, an array of floats from -1 to 1. Don't worry if it tells you nothing, we will cover it in a moment. Okay, so what is an audio signal? Well, it's just a wave, representation of sound over time. What we see in the y-axis, the amplitude, is a normalized representation of physical air pressure fluctuation. Our ears recognize the shifts in both directions, represented by positive and negative values, and that's how we hear. The higher the value, the greater the air pressure deviation. What we see here is a waveform, a representation of the sound in the time domain, as you can tell from the x-axis. This particular shape is a sine, the simplest possible sound, which isn't too pleasant, at least for my ears. As you can tell, the wave shape keeps repeating. The width on the graph is the time it takes until the next repetition, in this case about 2.3 milliseconds. This time is known as a wave period. It is the inverse of the frequency and it's measured in seconds. Just like we can present the signal in a time domain as a waveform, a very smart person realized we can represent it inversely in a frequency domain. This is known as a spectrum. Instead of an infinite graph over time, why not just draw a single vertical bar for the frequency our sign represents? Notice that the amplitude is a half because the other half would represent the negative frequency, which we don't see here. And what's that frequency? Well, it's just the inverse of the period. In this case, 440 Hz, so the A4 note. Real-life signals are rarely ever a primitive sign. When you play an A4 on a piano, it more likely will look like this. Fortunately, the same smart guy told us that any signal can be broken down into sine waves. So when we scrutinize that sound with a spectrum, we see just 4 vertical bars. These are harmonics, the multiplies of our frequency 440 Hz. Spectrum and the frequency domain are completely irrelevant to this game and deserve a separate video. Still, the most crucial bit is the duality of the signal and how the period is the inverse of frequency and vice versa. I keep using the terms pitch and frequency interchangeably, but it's time to get more precise. Pitch is our subjective perception of a fundamental frequency. And what's the fundamental frequency? It's the base frequency that defines the repetition rate of the waveform. Suppose you have these 3 different signals which you hear as 3 different sounds. They all share the same fundamental frequency, f0, which is 440 Hz. You will hear all of them as the same pitch. And the fundamental period t0? As always, just the inverse, so about 23 milliseconds. How do we know it? Because if you compare the first 2.3 milliseconds and the next 2.3 milliseconds and the next 2.3 milliseconds, in every signal, these are the same wave shapes. Even in the last one, which is decaying in volume, the shape clearly remains the same. So when we say pitch detection, we really mean finding the fundamental frequency. Given any of these waveforms, what's the algorithm? How do we find our f0? In other words, how do we find our t0? Well, we already performed it subconsciously. Our brain is really good with patterns, but if we were a computer, we would do it numerically by trying different periods. Let's start with this guess. We consider the following period about 1 millisecond, and then the next part of the graph, and then the next part of the graph. Not the best candidate, because when I compared part 1, part 2 and part 3 in any of the signals, I see very little similarities. So it was a pretty bad guess. So we keep trying bigger and bigger periods in vain until we hit the following. We try 2.3 milliseconds and compare it to the next part and the next part. Bingo! These are all the same shapes. Meaning our fundamental period is known. Meaning our fundamental frequency is known. And so we found, quotes, the pitch. The audio signals we looked at were all continuous functions, but this is not how computers work. We cannot record or store an infinite number of infinitely small data points. Instead, we can record amplitude samples at regular intervals, for instance every few microseconds. These are all graphs of how such discrete time signals look like. Notice how some information is naturally lost in the process, and even the periods are no longer so visually obvious. Okay, so let's just focus on one such signal. Remember the FFT size. This name comes from the FFT algorithm, which is probably computer science's greatest wonder, but that's for another video. What matters, however, is that it determines the size of our time buffer. And now you know what a time buffer is. You literally see its values in the graph above. We can check the sample rate. It says how often the audio signal is sampled, and we will need this value later. And it's almost guaranteed to be 44.1 kHz, and you can read online why is that. Okay, so knowing the sample rate, what's the sample period? In other words, how much time does a single bar cover on the graph? As always, period is just the inverse of frequency, and so the time between consecutive samples is about 23 microseconds. Now, this question is essential. Suppose we have a 1 kHz tone. How many samples are needed to represent that signal? So at least one period. Well, of course it's the period divided by a single sample period. And we know that periods are just inverses of frequencies, so we can rewrite it like this. And that's just sample rate divided by the frequency of 1000, which gives us at least 44 if not 45 samples to represent that sound. Let's go back to our pitch detection algorithm using this time buffer as an example. We said that we can keep checking the periods until we decide one of them is the fundamental period. So finally we get to this period. Notice that the period is now in samples, not in time. And we see that the second part is very similar, and then this third part is also very similar, and so on until we reach the end of the buffer. Conclusion? Yes, this is the fundamental period, 13 samples. But wait a second, what do we mean when we say that these subarrays are similar? The measure of similarity between two signals is known as cross-correlation. The equation is incredibly simple. Given the signals x and y, we just sum all the products of their corresponding elements. Quick intuition: big numbers of the same sign, big correlation. Small numbers, small correlation. Big numbers of opposite signs, negative correlation. And what's the Greek t known as tau? It's the lag. How much we want to shift the second signal so that they match. Of course, in samples. Okay, but we have just one signal, so what's the point? Same thing, we can compare the signal to itself, known as autocorrelation. It's exactly the same equation, and the second signal comes from a non-zero lag we choose. It shifts the original signal by tau samples, and that's how we get the new signal. Let's try it in practice for our lag, or tau equals 13. Multiply the 0th element by the 13th. Now multiply the first element by the 14th. And so on, and we hit the period and continue until we're done. The sum of all these products is our correlation. We obtain the highest correlation for this tau, 13, and so we conclude the fundamental period is 13. And here's the code doing all that. Let's analyze step by step. First, we define the largest and the smallest lag to consider based on the parameters. Maximum frequency and minimum frequency we handle in our application. Remember, we operate on samples, not on time, so we must convert the frequencies to samples using the sample rate, as we did earlier. Next, we consider all the lags in a loop. For each lag, calculate the autocorrelation by going through the entire buffer array. If the current correlation is the highest, save it and the lag. This is the potential winner. Finally, we need to convert our lag, measured in number of samples, back to frequency. Again, we use the same sample rate equation, just in inverse. And that's our pitch detection algorithm. The algo is beautiful in its simplicity and has exactly one issue. It is completely useless and won't work for our game. Real-life audio signals contain a lot of noise impacting the performance. It's even worse for a real-time detection because we run it every frame of our game. One of the possible fixes is to ignore the signals of weak volume and consider them noise. We can measure the average power or loudness using the root mean square. If it's too low, simply return -1, saying, hey, no pitch detected. Similarly, we can normalize our correlation with this equation and this code. Now, we have a correlation coefficient between -1 and 1. If it doesn't pass a threshold parameter we set, for instance 0.3, then we also return -1 to say we couldn't detect the pitch. With these fixes, our pitch detection at least somewhat pretends to work. Unfortunately, it is still far away from a playable game. It's still just as useless. Fortunately, there is a fast improvement of our autocorrelation algorithm known as YIN. Even though it doesn't use much more complex math, its performance is incredible. All the respect to these two gentlemen for such a brilliant idea. So let's go through the YIN algorithm and see how it improves pitch detection. Just like we did earlier, we consider a range of lags. Every lag is now called tau. First, for each lag, compute the difference function and store the result in the array D. This is just another way of measuring the difference between signals. Second, for each lag, compute what is known as CMND, cumulative mean normalized difference, and store it in the array D'. This is just another normalization technique. Next, find the first local minimum in D'. Given an array of numbers, what is the local minimum? It's just the number whose neighbors are larger. So we are looking to meet these conditions. Finally, one of the most brilliant yet simple additions, parabolic interpolation. When we select the best lag, let's say 5, we return sample rate divided by 5. This is how we convert samples back to frequency. But wait, who is to say that it's exactly 5? Why not 5.1 or 4.6? After all, the digital signal has a finite precision determined by the sample rate. Our samples are about 23 microseconds. This imprecise resolution is especially noticeable for higher frequencies. So the actual value we mean here is very unlikely to be an integer such as 5. More likely it's somewhere between 4 and 6. And this is where parabolic interpolation comes clutch. We can estimate the non-integer tau by simply assuming a parabola passes through these 3 points. Now, all we need is the minimum, which is the parabola vertex, and here we got it. We grab the x, and so the result is somewhere between our original tau and the next sample. And here's the final formula doing all this. We now get a much more precise tau. To sum it up, the Yin algorithm provides radical improvements while being minimally more complex than our original raw autocorrelation algorithm. It is absolutely suitable for real-time pitch detection, whether for human voice or musical instruments. Finally, let's glue all these bits together in a standard game loop. First, read user input. In our case, load the last audio snapshot into the time buffer. We can also already convert it to a frequency with our algorithm, so that our entire game input is just a single number. Next, update the game state according to that input. Finally, render the view based on the state. And what next? We keep repeating the very same sequence, and so on, and that's how our game loop looks like. And here's the code doing all that. As always, we track the delta time between the frames, and update the state proportionally to it. Okay, so there it is, our entire project, and we have all the audio related files in this directory. Similarly, all the shapes in this directory, so the cuboid, the gate, and also the sphere, which you could have also imported as a model, but here I wanted to use a procedure, so this is quite complex for the project. I didn't include it in the presentation. This is our entry index.html file, and inside of it we use ESM modules so that we don't need any build process except maybe for running the server for the static files. We also import the GL matrix using the import map. This runs natively in any modern browser. We have some basic CSS, our container, and inside of it the message to which we can enter this text for the syllable and also to say that we won. We have the game canvas, so where we render 3D. And these two elements are only in case we would like to enable audio graphs to see how the time domain and frequency domain look like when an actual waveform and spectrum. But that's about it, we can disable it. So this is the function that starts our game, and inside of it, unsurprisingly, we initialize all of the things and also start the game loop. So these are all the notes we have to sing. We can see them in the console, right? Next, we initialize the state, and when we look into the state, we have the game over timer, which says -1 that the game is still active, and it grows when the game is over, so that we can animate it. Current gate 0 because we have to pass it. Then we have the ball with the speed and position. This is of course just a vector 0, 0, 0. Then we have the gates. These are static, but I put them into the state just because it's very convenient. Next, we initialize all of the canvases. And as I've shown you, the waveform and spectrum canvases are only if we enable this flag. Next, we have our view, which is all about 3D rendering of our game. So there won't be any surprises there. Most importantly, we have drawing of the platform, the gates, and the ball. And this is all according to the MVPs. We have a separate MVP matrix for the ball and separate for the world, so that we can translate the ball model and world model separately. When the game is over, we can animate the camera so that it goes backwards. There isn't really much more to it, just a very primitive effect. This is rendering of the message, so the current syllable, and the game over message. We probably shouldn't do it every frame because it rarely ever changes, but it doesn't really matter much. And yeah, we have all the shapes initialized inside of the constructor, and that's about it. Next, we initialize the audio, and then there's our game loop. So inside of it, firstly, we calculate the delta time, how much time has passed since the previous frame. This is our audio input where we load the time buffer and can access it. As I said, we don't really need the frequency buffer. This is only if you want to visualize it. And next, we can directly convert the time buffer into a single number, which is the pitch, and I'm displaying it here, so as I'm talking or whistling, you will see the numbers. Next, we have the update method, where we actually update the state every frame according to the delta time and the input. And the whole input for our game is just the pitch, right? It's just a single number. So we can already cover what's happening here. There are just 4 main functions, really. We update the ball Y, Z, we check for the gate collision, and we handle game over if the game over timer says it's already game over. So let's collapse all of this and focus on just one each time. Firstly, we have update ball Y, which is just the rescaling function we did so that we can convert pitch to height using that pitch. The pitch is normalized so that it's in the range that we support in the game. And let's see why we don't want just to put the Y position into the new height. Let's see what happens as we do it. As I'm changing the pitch with my voice, you can see that the jump is immediate and it just doesn't feel right. Instead, we can use what's known as an exponential smoothing, where we just approach that value very quickly yet not immediately. So this is how the equation will look like. Let's say our smoothing factor is 0.2, and then we just keep updating the position towards that value very quickly, exponentially, and we reach it in very quick time, or at least almost reach it. So yeah, that's how we can do it. We can look into the, sorry, I need to import it. We can look into this and you see, okay, it's like 0.1. The higher, the faster it approaches, of course. Next, ball Z. This is nothing but just updating the speed and the position relative to the speed. There isn't much more to it. And the most important function probably is to check the collision. So we have the current gate, and if we are before the gate in terms of the Z position, then of course we don't need to do anything, we don't touch it. But otherwise we do touch it, and we have to check if our Y actually fits into the hole. So this is a very simple condition, just if our point is between these two lines vertically. If it is, then you see we pass it. And we also have cheating mode where it passes anyway. So if we did actually pass the hole, we increase the current gate, and if it's the final gate, then it means the game is over, right? Otherwise, we just bounce off the wall, and this is a very annoying gameplay feature, of course, because it gets really annoying when you cannot hit the pitch. I don't have this issue because I cannot hit any pitch, but if you can, this can be really annoying, but it is on purpose to make this game a little bit harder. And finally, the game over. We really just increase the game over timer. And I know it may look a little bit stupid, but this is purely for the sake of the animation in our view, so that, as you saw at the beginning of the video, we just want the camera to go backward to kind of show all the gates we passed. It's a little bit goofy, but you get the idea. Oh, and I forgot the most important. If you want to run this game locally, the easiest way is to just start a HTTP server with Python. This is really the easiest way, and when you do it, you can access it on localhost without any issues. And yeah, that's about it. That's the entire game. As always, thank you for watching, and let me know what you'd like to see next. Best of luck, bye bye.